Okay, let's go ahead and start the class. Today we are going to talk about dimensional analysis, chapter 7 of the book. We hopefully will finish this chapter today because it's a very short chapter. But if not, we are going to do, we're going to keep working on it on Tuesday, next Tuesday. But before starting the chapter, we need to talk about your second exam. So your second exam is scheduled to happen on April 22nd, which is the last day of the class. Okay. I was thinking we may need to go over the second exam before the final. So you may need some instructions, some help to understand the material a little better, right? So I was thinking of moving the second exam to April 20th, or I don't know how many of you celebrate April 20th, but I guess we can do April 15th as well. So the exam is going to be a little bit earlier, but we will have some time to go over the exam material and do a final review. Okay, what do you think about that? Okay, so let's see how many people do we have online. We have 5 people online. Okay, so let's see, which one do you want to go for, April 15th or April 20th? Does it matter? Or 15th, okay. Doesn't matter to anyone else? It depends. If you have finished the material, yes. But if not, we have to, there will be at least one lecture dedicated to exam review, okay? That's for sure. But the other lecture, if you have already finished the material, which I think we will finish the material a little earlier, and because there's only one more chapter that we need to cover, and I was thinking of covering some extra material, but then I decided against it. I think it's better to focus on whatever we need to learn and to make sure we learn them. Okay. So yeah, probably 2 extra lectures on exam review and solving example problems, but I can't promise anything else. Okay, so I think we only have one vote, one preference. I guess we're going to go with April 15th. Okay. I will send out an email as well. If you didn't receive any email from me, one of you who is in class, please remind me. But if you don't receive an email from me by Tuesday, please remind me, because these changes have to be on the books, right? I have to send an email. And yeah, so exam 2 will be on, it's a Tuesday, right? Or Thursday? Thursday. It's a Thursday. April 15. And we still have 4 lectures. So the exam will be exactly in 2 weeks, right? Hopefully we will finish this chapter today. We will start working on the pipe flow, which is chapter 8. On Tuesday, we will have an example solving session on Thursday, and then we'll do an exam review on Tuesday, if we could finish the pipe flow in 1 lecture as well. If not, then we will have 1 exam review session for exam 2. Okay. Any questions? Your homework also, I wanted to post the homework last week, and if you go to the syllabus, I was supposed to post it last week, but I wanted to include this chapter in homework 4 as well, because I didn't want to give you an extra homework, a homework 6, right? So homework 4 will be posted either tonight or tomorrow. So April 1st or April 2nd, right? And it will be due 1 week after the post date. So either next Thursday or next Friday, okay? And it will cover chapters 4, 5, and 7. So Reynolds transport theorem, the total derivatives, all of those things, the equations, integral equations, and the dimensional analysis that we want to talk about today. So if there's no other questions, let's start the discussion on dimensional analysis. The idea here in dimensional analysis, at the end of this chapter, I want you to understand what dimensional analysis is, or what's the importance of dimensional analysis, importance of dim analysis. I also want you to understand Buckingham pi theorem. I also want you to understand the importance of dimensionless parameters in fluid mechanics in general. Okay. So the topic of this chapter, we will mostly focus on the Buckingham pi theorem and how we can use that to simplify the problems in general. So let's start an example of fluid flow in fluid mechanics inside a pipe. Let's take a look at a flow inside a pipe. It is a steady. Let's assume this is a steady flow, incompressible, Newtonian fluid. Okay. So a steady state, incompressible, and Newtonian. And let's say we want to measure the pressure drop per unit length. So delta P of L, which essentially, whenever you're saying that you want to measure something per unit length, means that your length is a unit value. So your length here is 1 meters, right? We want to measure the pressure drop per unit length. And we want to characterize this. We want to see the dependence of this. What does this depend on? And how can we minimize or maximize the pressure drop? Usually you want to minimize this, the pressure drop. Okay? The first question you need to answer is, what does this pressure drop depend on? This pressure drop inside this pipe. So it's a function of a couple of parameters. What do you think? It's flow inside the pipe, and I'm pretty sure you have heard shear, wall shear a lot, right? Tau, u du dy, right? We have 2 walls here flowing inside the pipe. The radius is small, so which essentially means that your wall shear is going to be very important, which means that your pressure drop is definitely a function of viscosity, right? Again, we said wall shear is going to be important when you include the effects of viscosity. It's a pipe flow inside the pipe. There's no way for us to neglect those effects. So pressure drop inside the pipe is a function of viscosity. Okay? And what else? Usually your fluid flow is always a function of density, right? Density appears in all of the governing equations. And It's a very important factor. So your pressure drop is definitely a function of density. The dimensions of these pipes are also important. So diameter and the inlet velocity, V infinity, V. I think that ought to cover it, right? Your pressure drop inside this pipe depends on these 4 parameters. Again, our goal here is to let's say we want to do an experimental analysis, and we want to see the dependence. We want to investigate the dependence of pressure drop on all of these parameters. Okay? How many cases do we have to run to have a very good understanding of the dependence of pressure drop on all of these parameters? Right? We have 5 variables, dependent and independent. Your pressure drop is a dependent variable, right? And the rest of them are independent variables, right? What we can do is to fix the viscosity once, for example, change all of the other parameters, and measure the pressure drop inside the pipe. Then do it for density, then do it for diameter, then do it for velocity, and then do it for 2 of them, then do it for 3 of them, change the other one. So a lot of different cases, which essentially means that we have to deal with like 5 times. There are 5 different cases for pressure drop. I don't know if you have ever seen this type of analysis. Have you passed any statistics course? Yes? No? So we have 5 variables. All of them can be repeated 5 times. That's variable. So 5 to the power 5 is the total number of conditions we have to investigate, which is 625. Again, what does this mean? We want to experimentally investigate the importance of these independent variables in determining the pressure drop inside the pipe. To have a very good understanding, to have a comprehensive understanding of the importance of all of these parameters, we have to run this experiment at least 625 times, which is nonsense, right? It needs a lot of manpower, and it will cost a lot. So what can we do? One solution that comes to mind is to reduce the number of parameters, right? I think that's a very reasonable solution. You want to reduce the number of parameters. Are we clear on what's happening here? We have a problem. This problem depends on so many variables, right? Which means that we have to spend a lot of time to study the effects of all of those parameters, right? Variables. You just want to reduce the number of those parameters, right? That's essentially the idea behind the dimensional analysis. You want to make your problem depend on a smaller, fewer number of variables, right? You want to reduce the degrees of freedom. Does it make sense? Okay. So this is what we want to do. Let's move things around a little bit. What we can do is to define this new parameter, d multiplied by delta p, L divided by rho v squared. That can be a function of rho vd divided by mu. So what have we done here? We have moved things around a little bit, right, to come up with these 2 new parameters. At the end of this lecture, you will learn how to come up with these 2 parameters. So don't be, yes. Okay. This is not an example that. Yeah, I guess. Yeah. I can't hear you. You have to speak up. So this I want to employ this strategy that we are going to learn. We haven't learned anything yet, right? To this specific problem, right? But this is a very general problem, pipe flow, right? It's not like you have this velocity. You don't have any of the parameters. You just the only thing we know is that this is the flow inside the pipe, right? So we are not solving an example. We're just learning a strategy that can fit many problems, but we're just doing and this is how your book has done it. So I'm just following whatever they have. Okay, so if you wanted to reduce this number of parameters, this is what we could have done. We're going to learn how to get from here to here. That's the idea. And what does this mean? This means that we only have two parameters, one independent parameter, other one a dependent parameter. So we can get an idea of the pressure drop inside the pipe with just running one experiment, right? The only thing we need to change is this parameter, and then we measure this one, right? Which is going to give us an idea on how your pressure drop per unit length is going to change with respect to this other new parameters. Okay. Doesn't really matter how it changes. It's just an example. So again, just to make sure that we are on the same page, the idea here in dimensional analysis is to reduce the number of parameters, right? Which means that we are going to simplify the analysis, right? Instead of running 625 cases, we are just going to run a couple of them, like 5 cases, right? We are going to get 5 data points, and then do a curve fit, find the dependence of this on this, right? And we are going to keep the diameter rho and v constant, which essentially means that we are going to get an idea of the pressure drop inside the pipe. But the question is, let me ask you this. Do we understand what's the purpose of dimensional analysis now? Simplify the problem. Make the number of variables smaller, or deal with fewer number of variables. Okay? So that's the purpose here. But the question is, how should we get from this to this? That's the question we want to answer today. And we will definitely solve an example from this. So the method we are going to use to get from this equation, this more complex situation, to a rather simplified situation, is called the Buckingham pi theorem. Okay, Buckingham pi theorem tells us that you have to count the number of variables first. Right? How many variables do we have here? 1, 2, 3, 4, 5. The number of variables is going to be k. Let's say k variables. And then you have to find the number of primary dimensions that are present in this specific problem. What are the primary dimensions here? To understand the primary dimensions, you have to find the dimensions for each variable, right? So for velocity, what is the dimension for velocity? Meters per second, right? Both of them are primary dimensions. You remember MLT and FLT? We had this discussion earlier in the class, right? Mass length time or force length time, right? We had two different approaches to primary dimensions. Do we all remember these two? Or yes? No? If your answer is no, let me know. We will talk about it in more detail. Okay, so we all remember this, that we have 3 or more primary dimensions. Dimension of velocity, meters per second, or length per time, right? Dimension of diameter, meters, or length. And we are doing SI here. So dimensions of density, kilograms per cubic meters, or mass divided by length cubed. And then dimensions of viscosity. Who remembers what the dimensions of viscosity was? I usually forget this myself. It's kilograms per meter second, which means that it is mass divided by length multiplied by time. And the last thing you want to talk about is the dimensions of pressure, which is newtons per meters squared. Okay. Is newtons a primary dimension in the MLT system? No, right? Because primary dimension here is mass, not force. So we have to transform this to the primary dimensions. Newtons is force equals to mass multiplied by acceleration, so kilograms meters per square second, right? Just plug that in. It's going to be kilograms divided by meters square second, or mass length time squared. Okay. So how many primary dimensions are present here? We only have mass, length, and time, right? The other primary dimension that is also popular in fluid mechanics, is common in fluid mechanics, is temperature. Temperature is not present here. So number of primary dimensions present, which is going to be R, is 3, right? In this case, number of variables here we have is 5. Number of primary dimensions is 3, right? Number of primary dimensions. Again, the goal here is to get from this a more complex situation to a rather simple situation, okay? We want to employ that method. The first thing you need to do when using that methodology is to count the number of variables, 1, 2, 3, 4, 5, and then count the number of primary dimensions present. In most cases, number of primary dimensions present in your problem is just 3, MLT or FLT, depending on the situation. And then you subtract the 2 from each other. K minus R is going to give you 2. All right. This 2 is telling us that we can simplify this problem to be represented by only 2 new parameters. Okay? That's it. Number of new parameters. So far, we are consistent, right? We have seen here in the final solution that we have 2 new parameters. Over there, the Buckingham pi theorem has already told us that we need two new parameters. Okay. Okay. So what's the next step? How should we find those new parameters? That's the main thing you want to answer, right? Because at the end of the day, knowing that we can reduce the number of parameters, variables to 2, doesn't really help us. We want to find which 2 are going to be the parameters of interest, if you will. These new parameters are called pi's. That's hence the name Buckingham pi. So we are looking for a pi 1 and a pi 2. We want to find these two. One thing to keep in mind, and one clue you have in finding these parameters, is that these parameters have to be dimensionless, right? So we are going to change this problem in a way that will give us dimensionless parameters, okay? So first clue, that we want to keep the dimensions we want to keep these new parameters. We want to make sure that pi 1 and pi 2 for this case are dimensionless. And we're going to talk about why that's a very beneficial thing to do. Okay? Next step is to choose parameters, two parameters that are not going to be repeated, non-repeatable parameters. This is based on experience or based on, let's call it luck, non-repeatable parameters. What does it mean? We have two dimensionless new parameters, and we already have 5 other parameters. So there is no way that these parameters won't be repeated in these two new ones, right? We have 5 old parameters, 2 new ones. Is this clear up to this point, what we are doing? And here we want to find the 2, 1, pi 1 and pi 2. The idea here is that some of those 5 parameters should be repeated here, right? Because we are reducing 5 parameters to 2. So some of these parameters will be repeated. Like velocity, for example, can be represented in both of them. So these two non-repeatable, so we have to make sure that 2 of them are at least non-repeatable. I'm going to choose the pressure drop and viscosity. How do we choose this? Just based on experience, right? Or based on your problem. Doesn't really matter what you choose. As long as you follow the same procedure, you may get a different solution, but it doesn't mean your solution is wrong. You just have gotten a different solution. Some solutions are more common, so you probably want to follow the thing that people have already done, right? To make sure you get to the same solution. But there is no wrong solutions here. Whatever new dimensionless parameters you find is correct, right? As long as you have followed the procedure correctly. Okay, so the idea here, these two have to be present in the 2 new parameters. The other ones can be present or can be not there. Doesn't really matter. Or their power actually can be 1, 2, 3, 4, 5, whatever. The only thing that matters here that we are setting is that viscosity has to be present in one of the pi's, and pressure drop has to be present in the other pi. Okay, what are the other parameters we have? We have density, we have velocity, and we have diameter. Same is true. And these 3 are called the repeatable parameters. Okay, they can be repeated. Well, how can we make sure pi1 and pi2 are dimensionless? How can we make sure that's the case? This is what we do. We want to make sure that these two are present, but these can be there or cannot be there. Doesn't matter. So we take them to some arbitrary powers, A2, B2, C2. We don't know these, right? Just arbitrary powers. A1, B1, C1. Okay? And then your goal here is to choose these powers in a way that will ensure your pi1 is dimensionless. That's the next step. We already know that your pi1, the dimension of this pi1 is 0. Okay, so let's do this for the first one. What was the dimensions of delta p? I want to use MLT method. You can use FLT method, doesn't really matter. But this is the method I usually use for myself. And it is a more common method, so I'm going to keep using that. So what is the dimensions of delta p in the MLT method? Primary, based on primary dimensions. Mass divided by length divided by t squared, right? This is to the power a. Okay? Then that's actually this is 1 to the power 0. Okay, what else do we have? We have density. Density is mass divided by length cubed to the power v1 multiplied by, what else do we have? We have velocity. That's length per time to the power c2. What else do we have? We have diameter. That's length to the power d1. Sorry. Is there any questions up to this point? Right? We have taken this. This is that's my mistake. This, I'm sorry, has to be. This one is 1, then A1, B1, C1. Do we have any questions here? Let me rephrase the question. How confused you are? How confused are you? Not confused at all. One person is not confused. What about others? Yes.
So I understand what you're doing right now. So in a problem, though, would we be doing this as well?
Yes.
So I'm good right now.
Okay. What about others? Good. And I assume the rest of you are good as well. So okay, how can we ensure that this is the case? All of these powers combined have to be equal to 0, right? But on this one, we have 1 to the power 0, or we have 1. Whatever to the power 0 is going to be 1, right? So let's actually do this. We are multiplying some variables that are taken to the power something, right? Let's do for m. Let's actually let's expand this first. We have m. That's your dimension. m L T multiplied by m to the power a1 L to the power negative 3a1 multiplied by L to the power b1 T to the power negative b1, right? And L to the power c1. All of these have to be equal to 1. What does this mean? This essentially means that all of these primary dimensions, all of their powers have to be 0, right? Whatever to the power 0 is going to be equal to 1. So we have to rearrange this to get the powers for all of these individual things. So we have m to the power 1 plus a1, and that's it, multiplied by L to the power negative 2 plus negative 3a1 plus b1 minus or plus c1, right? And then we have t to the power negative 2 negative b1. Is this clear? I just combined all of these dimensions together, right? Then if you don't remember, like a to the power 2 multiplied by a to the power 3 is equals to a to the power 2 plus 3, right? Or a to the power. That's the idea here. That's the only thing I did. OK? And for this to be equal to 1, all of these powers have to be equal to 0. So 1 plus a1 has to be equal to 0. Negative 2 minus 3a1 plus b1 plus c1 has to be equal to 0. Negative 2 negative b1 has to be equal to 0. OK? So oh, yeah. So what can we conclude from this? It's pretty easy to solve. b1 is going to be equal to negative 2, right? a1 is going to be equal to negative 1. We plug those in. Negative 3 multiplied by negative 1 is going to be positive 3. We have negative 2 here. It will be positive 1. Here is going to be negative 1. So C1 is going to be equal to 1. Is this clear? So we have the powers we were looking for, which essentially means that we have the first dimensionless parameter we were looking for, pi 1. Pi 1 is going to be equal to delta PL, then rho to the power a1, which a1 is negative 1. So that's delta PL divided by rho, right? V to the power b1. b1 is negative 2. So that's v squared in the denominator. And then we have d to the power c1. The value of c1 here is 1. That's it. That's your pi 1. So we have succeeded in finding one of the pi's. And in an exam, if I wanted to give you this problem, I will probably only ask you to find one of the pi's, right? Not all of them, because it takes a little bit of time to get here. It's not that hard, but it just takes time. Are we clear on what happened? Yes. Yes. Yeah, definitely. Yeah, yes. Hi.
Where did the negative 2 on the L?
Negative 2 where?
The L, the negative 2 by itself.
That's right here. MLT, that's in your delta P, right? Just one of them. Oh, did I make a mistake here? I don't know. I have to calculate this again. What was the delta P is force newtons per meters squared, which is kilograms per kilograms per yeah, that's it should be -1, not -2, which means that your C1 is going to be a different value, right? That's -3 divided by -1, positive -2. So C1 is going to be 0. I probably have made a mistake somewhere else because your C1 has to be -1 or +1. Let me just make sure. Yeah, I mean, let's see what is it. Thanks for bringing up that mistake here. Let's see where we have made the mistake. That's MLC. That's -1, right? Yeah, -1, -2, -1, -3a. That's correct. Plus B1, L to the power B1 plus C1. Okay. I can't find the problem, but thank you for bringing this mistake up. And on my notes, actually, I've used the FLT method, so I can't go back to the notes I have. But it's just a stupid mistake. I'm pretty sure you can catch it if you go back to this. These are the final values we should get to. C1 is equals to 1. Where did we make a mistake? That's M, L, that's V, right? L, that's positive V1. V1 is -2. Just forget about it. Can't find it for whatever reason. Okay, so let's move on. Let's do the pi 2. Hopefully we won't have this mistake in pi 2. And let's do the pi 2. So for pi 2, we have the viscosity. Your pi 2 is going to be equal to viscosity multiplied by your density multiplied by the velocity and the diameter to the power B2. So your dimension 1 is going to be equal to dimensions of viscosity, which I keep forgetting for whatever reason. Dimensions of viscosity is m L T squared. That's to the power 1, right? Multiplied by density. That's m L cubed to the power A2, right? And multiplied by velocity. That's L divided by time to the power B2 multiplied by diameter, which is L to the power C2. Okay, so let's expand this. Your 1 is going to be equal to, I'm just going to use the powers of m to the power 1 plus m a2 plus, that's it, right? A and m2, right? Then multiplied by, we have L again, L negative 1, negative 3a2, positive b2 plus c2, right? Multiplied by your third primary dimension time. We have negative 2 and negative b2. Negative 2, negative b2. Let's see what is going on here. That's the mistake. That viscosity is m divided by LT. That was my mistake. So the negative 1 minus b2. Maybe, but we don't have viscosity over there. Just you make sure that your dimension, whenever you're solving the problems, you should make sure that the dimensions are correct. Okay. So what does it mean? This has to be 0. A2 plus 1 is equal to 0. Then this part has to be 0. Minus 1 minus 3a2 plus b2 plus c2 is equal to 0. And b2 is equal to 0. Which means that your a1 is negative 1. Your b1 is also negative 1. Your b2, I'm sorry. These are our 2. And let's plug that in here. Negative 1 is positive 3. Negative 1 here, negative 2. C2 is going to be equal to negative 1 as well. So your pi 2 is going to be equal to viscosity divided by rho v d. That's it. We have the two-dimensionless parameters we need to analyze problem. Usually the more common dimensionless parameter that we use here is 1 over pi 2, which is rho vd divided by mu, or the Reynolds number. Is this clear? Is this methodology, is this whole thing? Do you understand how to apply the dimension analysis, apply the Buckingham pi theorem, and do this type of analysis? Again, you don't have to use the MLT system for primary dimensions, but you can use the FLT system, just have to be consistent. So if your primary dimensions are force, length, and time, you have to change your, wherever you have mass, you have to somehow bring in force, right? You have to change all of the dimensions. So in my mind, it's easier to go with MLT because we have all of the things except for like force itself is based on meters and seconds and kilograms, right, in SI, or slugs or whatever in the British units. Is there any questions? No. Okay. So as you can see, as I said, we have these, we call them dimensionless parameters, and these parameters show up a lot in fluid mechanics and also in heat transfer, which you are going to take next semester. And hopefully, you haven't registered yet, have you? No, pretty soon, hopefully. Let's actually see a list of these dimensionless parameters. Uh, just see, let's see a list of them. Mechanics, S21, lecture. Node 19. I'm going to upload the lecture notes for sure, but just in case. These are the most prominent dimensionless parameters that you are going to see in fluid mechanics. We have seen Reynolds number a little bit in chapter 1 and 2. You have heard the name. Pretty sure we solved an example using the Reynolds number. And Reynolds number is rho v multiplied by your length scale. It can be length, it can be diameter, depending on the type of flow, divided by mu on the top here, right? Reynolds number, which essentially is going to give us the ratio between the inertial forces and the viscous forces, right? Which one is more dominant? Higher Reynolds number means that your inertial forces are going to be more dominant, right? Reynolds number is used usually to distinguish between a laminar flow and a turbulent flow, right? We usually, in different types of flows, we have an onset of turbulence. Have you heard the names laminar and turbulent flows at all? Yeah, you don't need to know what they are, but as long as you have heard the name. We have the onset of turbulence or onset of laminar flows, and which can be distinguished based on Reynolds number. For example, Reynolds number on a flat flow over a flat plate, which is very common in like aerodynamics. You have flow over wings, right? We can assume that those are flow over a flat plate. Your flow starts to become turbulent when your Reynolds number reaches 5 times 10 to the power 5, right? That dimensionless parameters. This is something that we can apply anywhere. You can apply it to a very small test section inside a wind tunnel for an aircraft, for example, or you can employ it on a real wing, right? That's the beauty of the dimensional analysis, that you can do the analysis for a very small wing in a wind tunnel, and then you can apply that same analysis to a huge aircraft, right? Because you have removed all of the dimension dependence here, right? Okay, and the other parameters, like we have the fraud number, fraud number, which is hopefully we're going to see more of fraud number later in this course. You have the Euler number, Cauchy number, Mach number, Extruhal number, Weber number, all of those things, right? But the number that you have to be familiar with is the friction coefficient later in life. In heat transfer, friction coefficient is going to become very important, as well as the Reynolds number and Nusselt number, which is something you're going to learn in heat transfer. Is there any questions here? Okay, so do we understand the dimensionless parameters? Let's actually discuss the dimensional analysis a bit more, and then I'm sorry. Okay, so we understand how to find the dimensionless parameters that are important for that specific problem. For example, these two dimensionless parameters are very handy when you want to investigate the pressure drop inside a pipe, right? Which is a very important actually parameter when you this part of the analysis is actually a very industrial analysis, because this is something, the pressure drop in a pipe is very important when you're designing pipes for a building or whatever, right? Or the pipes that can transfer oil or something, right? So hopefully you understand how to find the important dimensionless parameters here. But the next thing I want to talk about, and this is, the concept itself is pretty simple. And I just mentioned it a little bit. The idea is the scaling. When you are using dimensionless parameters, right, you can test, again, let's go back to the wings and aircraft. You can test a small wing in a specific flow, and then you can apply whatever you have, whatever the results of that study is, to a bigger wing, a real-world wing, as long as their dimensionless parameters, their important dimension parameters, remain the same, right? So for a wing analysis, Mach number is important. That's velocity divided by the speed of sound, Mach number. And Reynolds number is important. So if you are rho v, rho vl divided by mu. If you are doing the analysis inside the wind tunnel, you can use the same results for designing a real-world aircraft, a real-world wing with the huge dimensions, as long as in that real-world case, or the operational velocity of that real world has the same Mach number as your test section and has the same Reynolds number as the test section. Does this make sense? Okay, so one question can be that I may ask you, or you may actually see this question later on in your life, is that you are given a velocity inside the wind tunnel, density, area, all of those things, right? You are given all of the parameters you need, and you are told to find, you are given the velocity for a real world case, and you are told to find whether these are the same case, essentially, and when it comes to dimensionless parameters. You just have to calculate the dimensionless parameters and make sure they are the exact same values, right? Then you can say, I can apply the results from, I can get the results from this test section and apply it to the real world situation. Okay. So let's I don't want to solve another example, but since I forgot to, I just want to talk about it a little bit. So, and I forgot to give you a printout of the example. So I'm just going to write the text on the board, just to make sure that we are following. Okay? So we are given a thin rectangular plate. Okay? Having a width W, and height h, is located so that it is normal to the moving stream of fluid. Moving stream of the fluid. Okay? And it is shown in a figure. You want to assume the drag force drag D, that the fluid exerts on the plane is a function of W and H, is a function of W and H, and the fluid velocity and density and the fluid viscosity. It should be also density, velocity, right? And the velocity, yeah. And the velocity of the fluid approaching the plate. Okay, you want to find the suitable set of pi terms. Find a suitable set of pi terms that to study this problem experimentally. To study this problem experiment. So, are we clear what the problem is? We have a thin rectangular plane that is normal to the upcoming stream. So it is like this, and the flow is approaching this. We are told that the drag force is a function of W, H, mu, rho, and V. Okay? The first thing you need to answer here is, what is the drag force? Do you know what the drag force is? Have you ever heard about this force? Yes. So what is it? Can you tell us?
Drag is basically the resistance, I guess. Almost like you move something through the air doesn't necessarily want to get out of the way, so you have to force it out of the way.
Okay. Exactly. That's the idea. So drag, if you want to become a little more mathematical, is the force that is being exerted on the plate by the flow in the direction of the flow, right? So essentially, if you have this type of flow, you are pushing the plate back, right? You're pushing the plate back, and that force that you are exerting on the plate is called the drag force, right? If your force is normal to the plate, which is something that may happen, that force is called lift, right? So that's the only special thing about drag. Drag is a force exerted on a body, right, that is in the direction of the flow. And that force, we are told that is a function of the width and height, viscosity, density, and velocity. Okay? Okay, velocity. So let's say we want to start the Buckingham pi theorem analysis. What should we do? The first step is to count the number of variables you have. One variable is the drag force itself. Another one is the width. The other one is height, density, viscosity, and velocity. So how many variables that is? 6. So your K is equals to 6. The next step is to determine how many dimensions, how many primary dimensions are present here. How many primary dimensions are present here? Your drag force is force, so newtons, and newtons in MLT we found is kilograms meters per second squared, right? All of which are primary dimensions. Then your width, the dimensions of width is meters. Again, we are dealing with SI. You can also use the British units, doesn't really matter. You should get the same results. Height is also meters. Density kilograms per cubic meters. Viscosity was kilograms per meters second. And velocity, meters per second. Okay, so how many primary dimensions do we have here or present here? 3, right? That's usually the case. R equals to 3, which means that the number of pi terms, is equals to 6 minus 3, 3. So we can reduce the variables from 6 to 3 variables, right? That's the idea. What is the next step here? The next step is to choose the non-repeating variables, right? The idea over there was that you have to choose them based on experience, right? So essentially means that you can choose any variable you want. But I would say whenever you have the presence of viscosity is usually one of your non-repeating variables. So you want to keep that there, one of the non-repeating variables. We have 3 pi's. Again, we have 3 pi's. We have to choose 3 non-repeating variables. So first one, viscosity. Second one of the non-repeating variables I want to choose is the drag force itself, right? Because that's the thing that we want to investigate. And if I were to choose another one, I would have chosen the width of the system. I don't know. I don't have the solution what your book has chosen. But again, as I said, it doesn't really matter what you choose. As long as you can reduce the number of parameters, you have a correct solution. Okay. And in an exam or homework, not probably in homework because I don't grade the homework, and your grader uses the solution I provide. But in an exam, if you follow the procedure correctly, you will get the full grade. If you just come up with a nonsensical dimensionless parameter, doesn't really matter to me as long as you have followed the procedure correctly, okay? Because there is no wrong solution here, all right? If you come up with a nonsensical dimension, by nonsensical, I mean something that is not common. The other 2 pi terms are going to be uncommon as well, right? If you come up with a Reynolds number, the other 2 will be common dimensionless parameters as well. Okay, so I'm going to choose these 3, right? And what is the next step? Your pi 1 has to be equal to mu multiplied by the other parameters that are there, your height, density, and velocity. So mu h to the power a1, density to the power b1, and velocity to the power c1. Pi 2 is going to be equal to d, h to the power a2, rho to the power b2, and v to the power c2. Pi 3 is going to be equal to your width, h to the power a3, rho to the power b3, and v to the power c3. And you can just do the rest, right, to find the pi theorems, to find the pi parameters. Is there any questions here?
So it doesn't matter which ones we choose.
It doesn't matter, yeah. I mean, at the end of the day, it doesn't really matter which one you choose. But let's put it this way. This is for experimental analysis, right? And you can do an experimental analysis based on your own set of dimensionless parameters. But if your own set of dimensionless parameters is different from someone else's, you won't be able to compare your results, right? That's why you want to remain consistent with others, right? That's why you want to follow what others have done, because you want to be able to compare your results, okay? But from the perspective of this course, it doesn't really matter. Okay, so that's it for chapter 7. There are some parts of chapter 7 that uses, like half of chapter 7, that uses some material from chapter 6, which we didn't go over. And we are going to start working on chapter 8 next lecture. These are short chapters. Like chapter 4, chapter 7, and chapter 8 are very short chapters. If you recall, chapter 4 didn't take us that long as well to finalize, and just 2 lectures maybe. Chapter 8 is also a short chapter. If you could finish chapter 8 in time, if you had enough room to do like reviews and solve example problems, I would go back to chapter 6. Chapter 6 is something no one really covers, but I think is an important chapter. So you will get into trouble in your like future courses if you don't have any idea on what's going on with the like partial differential equations in fluid mechanics. You should at least have seen those equations. That's it. So probably, if you have enough time, we'll probably just one lecture. I'll just go over them, show them to you, so you have some exposure. And yeah. And an exam is going to be on the 15th. I will send an email. If I didn't by Tuesday, when you come into class, please remind me. And one other point is that we haven't had enough attendance quizzes. So just a heads up, I guess, to everyone. The rest of the class, every class, we will have an attendance quiz, right? So if you don't send an email to me to either have a justification or come up with a justification, doesn't really matter. As long as you send an email to me, I usually don't ask for proof. It depends on the situation. And don't come to class, you will lose that attendance point, right? Because we haven't had enough of those. And that's, I think, 10% or 5% of your final grade, right? It should be graded based on something. And there are a couple of you, I mean, all of you who are in class are usually in class. So I don't see how, if you miss any of the future lectures, you will lose any attendance points, right? So this is something for the rest of the class who are not here. And I guess that's it. Yes. 4, 5, 7, and 8. If you could finish all of those. We will, yes, for the exam 2, yes. I mean, you won't get a study guide. Yeah, practice. So the same thing we did for the exam 1. Okay. When? So my plan at this point is to finish chapter 8 next week, and then do the example solving session on Tuesday. So in 12 days, right? I will give you the practice problems then. But if you want to have them sooner, I can post them sooner on the website as well. Okay, I will. So this time, last time I solved, I guess, problems that are more complicated than the exam, right? Those problems were definitely more complicated than the exam, and it ended up not being very helpful, because I guess a lot of you were confused with those complicated problems and didn't help you with the simpler concept that showed up on the exam. So we'll make sure to include, to start from simpler concepts and build up on it, right? to get to. If you had enough time, we'll solve more complicated problems as well. If not, then, but the exam, let me put this way. Exam 2, I know you guys felt that exam 1 was challenging, and what I'm going to do for exam 2 to make it less challenging is to make sure that I mean, you have to tell me that if you don't understand the concepts, right? I don't have any way of knowing if you. But I'm trying to focus on the basic concepts a little more than just the more complicated concepts, right? And hopefully that will help you understand the basic concepts a little better, right? And this is what we're going to do in the example, in the review session as well. We will focus on the basic concepts and we'll build on those. But the level of difficulty of the exam 2 is going to be the same as exam 1, right? And by that I mean as long as you understand, right? The problem with exam 1 was that a lot of you didn't understand what the question is asking you to do, right? It's just like some of you didn't understand what dimensional homogeneity is, which we had covered in class, but I guess I should have put more focus on it, right? And it was part of one of your homeworks too, right? Or a lot of you couldn't make the connection between the bulk modulus and the problem too, right? If you could, then it was just one equation, plug in numbers, and it was it, which was the case for a lot of people. So the level of difficulty is going to be the same as exam 1, right? But I will try, I guess, harder to make sure that you can make the connections between the problems and the equations, right? So just copying and pasting equation on your exam sheet is not going to be very helpful. You just have to make sure that you understand what does this equation mean? What does this equation do, right? When I say Bernoulli, what does Bernoulli do? I mean, you have pressures at 2 points, velocity at 1 point, you can find the velocity at the other point. That's what Bernoulli does, right? But whenever you're given this type of problem, use Bernoulli, right? That's it. Whenever you're asked to find the pressure needed to change the volume, that's the compressibility problem. You want to get to the bulk modulus. So we are going to focus on these type of things a little more. Okay? Yes.
Will it be the same style as when like you have a few concept questions where you just explain, or will it be more solving?
Which one do you prefer?
Just wondering so we can prepare.
Okay. That's actually.
So I'm asking like, will we have a favorite concept?
Yeah. So I'm going to ask the question from the class. Which type do you prefer? Do you want to have concepts plus some problems that you need to solve, or do you want to have only problems that you need to solve? I personally would rather to give you a problem, an exam that has both of them, maybe fewer number of questions, right? That can like fit the time scale, like 75 minutes, maybe like 3 problems that you need to solve and 3 conceptual problems, something like that, instead of, how many did we have? We had 4 and 4, right? So maybe 4 and 5, but maybe 3 and 3, right? This is what I'm thinking right now. But if you have a different preference, if you would rather see like 4 problems that you need to solve and that's it, you can let me know. At the end of the day, exams and grades are not the main focus here. The main focus for me, at least, is to make sure you guys are going out of this class with some fluid mechanics knowledge, right? Which is, you may disagree with my goal. You may just think of the grade, but that's my goal. That's usually my goal for all of my classes. So don't worry about the grades. I will. Yeah. So if you have a preference, I guess you don't have a preference. Okay. Let me know. That's it. Have a good day. See you next Tuesday. Homework will be posted today or tomorrow. It will be due next week.